Sanbonana. Hope the right. We're just gonna continue with calculus. We're still under calculus, still under derivatives. Now we will be doing second derivative. Now the equation is, what is the second derivative? Now second derivative is just derivative of a derivative. We denote it. I hope now we know the derivative is just f prime. Say they say f prime of x. Now the second derivative is just f prime prime of x. So it's a derivative. It's a derivative of a derivative, meaning you derive two times. Kabili, you derive the derivative. Let's just do an example here. Minus 5x squared plus 3x. And then let's say now we derive, let's say they want the derivative. The second derivative. Before you get the second derivative, you must get the first derivative. So getting the first derivative, which is 3x squared and minus 10x plus 3, getting the second derivative. Now I hope you know what is the first derivative. What is the first derivative? Getting the second derivative. Now deriving again, it's just gonna be 6 minus 10. That is the second derivative. Now the question is, what is the second derivative? What does the second derivative do? What is the purpose of finding the second derivative? So going there, we're just going to do the graphical. Just going to explain the purpose of second derivative by doing the graphical interpretation. I'm just going to explain it. What is the purpose of the second derivative by doing this, the graphical interpretation of the second derivative. So first thing, the second derivative is a measure of the concavity of the of a function. Is a measure of the concavity of a function. What does that mean? So if the graph of a function concave up, the function is said to be concave upward. If you peg a pencil like this, the function is said to be concave up. Or if the function is said to be curves, if the function is curve up, it's said to be concave up. So if peg a pencil, or if function is curve down, it says to be and concave down. But let's just do some little bit clear example of what is explaining the concavity. But now if the second derivative now of a it's greater than 0. Now the second derivative, remember the purpose of second derivative is to find the concavity of a graph, the shape of it, of does it concave up, does it curves up, or does it curves down, at the purpose of finding the second derivative. So if the second derivative of a is greater than 0, meaning then the f function, which is the original function, not the first derivative but the f function, is concave up. It's concave up if the second derivative of a is greater than 0. It's positive, mkhulu kuno 0. Let me just do a graph here where we have a function like this. Now I hope you see from here to here where it's second derivative at the point, this one, point A. This is where we find our second derivative. I'm still gonna explain what is the second derivative in terms of the inflection point, because it said something about the inflection point. But here I hope you see the shape here, a little bit concave up, ibheke phezulu like this. So from here, the shape here, it's concave up. So f is concave up at x is equal to a. I hope you see that one. I hope you see that one. So let's do another example. If f of a is less than, now ncane kuno 0, 0 mkhulu, meaning it's negative, then f is concave down at x is equal to a. At x is equal to a. We can have another function here explaining that. From this a now, the concavity starting from here going down. I hope you see now the shape. It's like it's upside down, ibheke phansi like this one. So it's a concave down, it's curved downwards like this. So f prime of a is less than 0. So f is what? It's a concave down. Concave down at x is equal to a. I hope you see that one. I hope you understand that one. Let me just make another point there. A point where a function changes from concave up to concave down. Or vice. And then from here the point where the function changes from concave up to concave down, or vice versa. This is called a point of inflection. I'm just gonna write the function. It's just gonna write it as the same as this one, but now explaining this point of inflection now. Where we have A this side, so now here coming to this one, and then this one. This point here, that's what we call the point of inflection, because now we started by where we have this shape here at x is equal to a, and also here where x is equal to a. But now what is this x? What is this x is equal to a? What is the name of this point where everything, the concavity, starts to change? Now you hope you see the difference now between the turning point, which is this one, and the concavity. Now that's where the concavity of a graph changes. The inflection, that's where the graph inflect. Here, the shape of it, from here to here to where it was concave down, concave up. From now to this point, going to this side, now it's concave down. So that's where the inflection point is. That's what the purpose of inflection is, to check the inflection, to check where the graph changes its direction. That's where the direction of a graph, it was increasing in terms of the concavity, and then here it's changed, it's gonna go the concave down in terms of the concavity. I hope you understand it one, because here concave up, this one is just concave down. This point we call the inflection point. So F as a point of inflection at x is equal to a. How do you find this point of inflection? By doing the second derivative. You derive and then you derive again. You derive 2 times to find the point of inflection. That's how you find the point of inflection. There's the note here, which is something that is very important. Just write it down. The fact that a second derivative equals 0 at a point does not always guarantee that the point is a point of inflection. To verify a point point of inflection of a function, we have to check the function, it's concave up or concave down. So to verify the point of inflection of a function, we have to check the function, it's concave up before the point and the concave down after the point. So to verify that a point is in fact a point of inflection of a function, we have to check that is a concave up before and concave down after the point, or vice versa. So we need to verify the point of inflection by checking the concavity. It's not always it is, you must check the concavity to make sure that your point of inflection is not always guarantee when you do the second derivative is your point of inflection. Okay, thank you so much guys for listening. Now we're going to do the practical example of this thing. Now we're going to do the practical of it just now. Thank you.